Okay, again, last time we talked about the structure and nomenclature of alcohols. Now we can have a 1 degree, 2 degree, 3 degree alcohol, now depending on where your OH is bonded to your carbon atom. And then we also have, we talked about, 1 degree, 2 degree alcohol. And there's another kind of alcohol. We call this one a phenol, where it's the OH is bonded to a ring. And then an alternative or a similar structure to alcohol is the ether, but instead of the hydrogen, there is an R group attached to your oxygen. So 2 R groups are attached to your oxygen. And for the nomenclature of alcohols, you can go back to your organic chemistry 130, naming different functional groups, different class of organic compounds, how to name our alcohols. But to review for that, we've learned that to name alcohols, we always end with an O when we name our alcohols. And the longest continuous carbon chain that contains your alcohol, if there are no other functional groups present, like say carboxylic acids or other functional groups of higher priority, then our name will still end with O. And depending on whether we have 1, 2, 3 alcohol O, so we have to indicate if it's 3 OH on the longest continuous carbon chain, so you have to indicate all the trione, so on. So if you want to review more on how to name, again, I'd like to encourage you to return to your previous discussion on how to name our alcohols. And last time also, and for the nomenclature of ether, we've also learned to name our ethers by substitutive way of naming or by functional way of naming. So you can have your ethoxyethane, for example, you can indicate your functional name, like you have to indicate your ether depending. So substitutive, you always indicate your OR to be ending with oxy. So for example, here you have CH3O, you have your methoxy, CH2, CH3O, you have your ethoxy. Again, to name ethers, you can review on naming organic compounds. So you can also name your ethers if it's in cyclic ring. So you just have to, there's a common name for most of the ethers that are cyclic. And for example, no, oxa, cyclopentane here. Oxa, it means that you have your oxygen in the ring, cyclopentane. Okay, so the carbon is substituted with oxygen. You have your octocyclopentane. The common name for this is tetrahydrofuran or THF. Commonly, if you are doing your laboratory work, and usually this is the common solvent that is used when doing some kind of reactions in the organic. Also this dioxane, so 1,4-dioxa, oxa for the ether, cyclohexane. So you have your cyclohexane, but the carbon is substituted with the oxa. So you have 1,2,3,4 oxa, dioxa, 1,4-dioxa cyclohexane, or the common name is 1,4-dioxane. Okay, so for the properties of alcohols and ethers, we have already discussed that last time, and we have already indicated that ethers have excuse me, ethers have boiling points that are roughly comparable with those of hydrocarbons at the same molecular weights, and we have learned now that
Excuse me, naka-presentation, wala may nakita.
Yes, naka-presentation. Pag wala sa internet, mawala pa daw ko. Nakita ninyo akong presentation?
Nana, ma'am.
Kagani, wala.
Nana, ma'am, thank you.
Kaganina, wala. Anyway, this is just a review. We have already discussed this one. And we will focus on today for the naming, but I'm not naming the chemical properties of alcohols and ethers. No? And last time we talked about the physical properties again, due to the hydrogen bonding that would be exhibited between alcohol molecules. No, alcohol molecules would have higher boiling points than comparable ethers or hydrocarbons of comparable molecular weights. Okay, and ethers, but for ethers and hydrocarbons, they have actually comparable also boiling points. But we're talking about alcohols with respect to other hydrocarbons or ethers having comparable molecular weights. Now, we always expect that alcohols would have a higher boiling point. That is, again, due to the hydrogen bonding that would be exhibited between the alcohol molecules. And as we know that hydrogen bond is much, the strength of the hydrogen bond as an intermolecular force interaction is much stronger than the dipole force of interaction or the van der Waals force of interaction. And again, that would affect on the properties of our alcohols and ethers. So for instance, now the molecular weight of diethyl ether is 74, and let's compare that one to butanol, 1-butanol. You can see that diethyl ether and 1-butanol, you have here CH3, CH2O, CH2, CH3, and 1-butanol, they are constitutional isomers. Now they have comparable molecular weight, they have actually the same, just comparable. And you see that the boiling point of butanol here is 117. It's very high, and diethyl ether would have 34.6. And when you compare diethyl and pentane having comparable molecular weight, they actually have also comparable boiling point, no boiling point, melting point. But for alcohol, and you compare that one with either ethers and the hydrocarbons, always the alcohol would have a higher boiling point. And again, that would be due to the type of intermolecular force of interaction that would be exhibited between the alcohol molecules. And with respect to the solubility of ethers and alcohols, you expect that ethers and alcohols are able to form hydrogen bond with water. And because of that, you expect that the ethers and alcohols to be soluble in water. The reason that they are miscible with water is because of the hydrogen bond. So ethers have solubilities in water that are similar to those of alcohol of the same molecular weight and that are very different from hydrocarbons. So even if ethers and hydrocarbons would have comparable boiling points, but with respect to solubilities, ethers would be soluble in water, and hydrocarbons wouldn't be soluble in water. Again, because of ethers, there is a possibility of hydrogen bond between ethers and water. So, nga naman na siya. If you look at the structure of ethers, let's see. Like say here, you have your ethers. Now you have your ether having an oxygen. You expect your oxygen to be partially negative, would bear a partial negative charge. And because of that, this molecule, the ether molecules, would exhibit rather dipole kind of interaction between molecules. So if oxygen atom would be partially negative, now it would exhibit hydrogen bond with water having hydrogen that is partially positive. So between oxygen and hydrogen atom, then that there will be kind of hydrogen bond interaction, and then that would allow the ether to be miscible or soluble in water. So, and of course, as we expect, the solubility of alcohols and also with ethers, as you increase on the number of hydrocarbon portion, katong R-group niya, expect also the solubility to decrease. And if you have a shorter length of the hydrocarbon portion, you expect your alcohol to be more soluble. And long chain alcohols are more like alkene-like, molecules na. They couldn't be, that means that the alcohols would have lesser solubility in water. Okay, so I think I have given this as an example in the previous meeting. Now let's go to the synthesis of alcohols. Now, last meeting, we talked about the different kinds of reactions that we have already encountered in chapter 8. No? And usually the alcohols can be prepared from our alkanes. Okay, and we learned that the general reaction to prepare an alcohol is the acid addition of water into our alkane. Acid catalyzed hydration of alkenes. So we add water to our alkene, and that's a hydration kind of reaction in the presence of an acid. And you always get the HOH, your alcohol. And of course, this kind of reaction would follow the Markovnikov's rule. And so how would it happen? Of course, we remember your chapter 8, no? First one is the use of an acid, no? Like say the proton, and our nucleophile will be from the electrons coming from the double bond, from the pi band. So one of the carbon will form a bond with the proton, with the hydrogen from the acid, and you'll have a carbon-hydrogen bond you have here. And one of the carbons, they utilize, of course, the bond using the pi electrons, okay? And one of the carbons would form a new bond, carbon-hydrogen bond, and the other carbon atom would bear the partial positive charge. And of course, again, when we have this acid catalyzed hydration of alkenes, do not forget to know on the mechanism behind this one. We always form our carbocation as our intermediate. Okay, and once you have your carbocation, then you can have your water added to your carbocation. And we will utilize the electrons in the water to our carbocation. Okay, the water will become our nucleophile. And what happens is that you'll form a carbon water bond, and oxygen having 3 bonds would bear the partial positive charge. And of course, to remove this one, we simply have to deprotonate our alcohol. So we have this as protonated alcohol. So we have to have a further deprotonation process of our alcohol, and simply we just use water to deprotonate this one, to abstract this proton using again the electrons of water, and you have this. And once the water abstracts the hydrogen here, then the electrons from O hydrogen will go to your oxygen, and you'll have, of course, two pairs of unshared electrons, and of course one of the products here will be the H3O+. Now once this one is abstract. And of course, you know, they have the Markovnikov reduced selectivity, you have free carbocation intermediate, and once you form your carbocation, there is always the possibility of the rearrangement of your carbocations. You see this carbocation here. If, for example, you have your R groups in your adjacent carbon, and if there is a chance that your carbocation would form a more stable carbocation, for example, you can carbocation, there's a possibility that there is a metal shift or there is a hydrogen shift. In order for your carbocation to be more stable, then rearrangement would occur. Any mechanism that would stabilize your carbocation would lead to the formation of an intermediate leading to your product. Okay, and next one is another kind of reaction is the, of course, oxymercuration, the mercuration process. There are 2 steps that's involved actually in the process. You have the mercury. We have already discussed this last time. Do not forget on how to prepare your alcohol. The first one is mercury acetate in the presence of water and THF. And this one, it follows the Markovnikov still reduced selectivity, but the first step, once you have your mercury, is that the positive, the mercury is the one which is an electrophile. Now the electrons coming from here from the double bond will add to the mercury acetylene. If you remember on the mechanism and how this oxymercuration, demercuration occurs, and the carbocation will be attached to your OH. Okay, and once we reduce this mercury acetate here with sodium borohydrate and sodium hydroxide, then you can reduce this to form your hydrogen. And of course, in the process, we will recover mercury metal. Okay, so Hg2 plus na yung siyang H2 plus. Again, it follows the Markovnikov bridge selectivity, but it has an anti-stereo selectivity. It can. And the only advantage of this, with respect to the acid catalyzed hydration process of preparing alcohol, is that it doesn't follow rearrangement. So there is no complication leading to the rearrangement. For example, if you expect the reaction to have a 2-degree alcohol, no, it wouldn't have a complication that there will be rearrangement, and you would, instead of a 2-degree alcohol that you would expect, no, the 3-degree alcohol would be obtained if you would have been using the acid catalyzed hydration. Another way of preparing your alcohol is the hydroboration oxidation process. And again, there is two reagents that's needed to proceed with the reaction. So I would like you to always be conscious in the second reagent, no, because without the second reagent, then we wouldn't be able to reduce this mercury here, and you didn't get the hydrogen. So there's always 2 steps: the mercury acetate, the presence of water in the HF, and then the second one is the reduction process. Sodium borohydride, always have to remember sodium borohydride is a reducing agent. So another one is, again, hydroboration oxidation process. You have your H3, H2O2, and then of course you will add your HOH in the double bond. Okay, and this one, the only thing here is it does follow the anti-Markovnikov addition. So instead of the rich gets richer and the poor gets poor, no, for our carbon atoms. So what happens is that it is the other way around, rich carbon. So you just have to take note of that. And then you have a syn stereo selectivity. So this one, this OH and hydrogen, it will add on the same side. Okay, if you look at the mechanism. And for this oxymercuration, demercuration, it doesn't follow. You wouldn't know if they're on the same side or not. Okay, but just know that for the hydroboration oxidation process, they always follow using the syn stereo selectivity. And as for the mechanism, again, you can review on the chapter 8 to remember on how the mechanism, what would be the mechanism to yield the expected product. Okay, so remember, if you have your double bond here and you have 2 kinds of alcohol that will be obtained, no? So one will be added, the OH will be added to this carbon here containing a higher number of hydrogen, and the other one will be, this carbon here will have the hydrogen being added, no? And the other carbon here containing the R will have the OH being added, no? And this one would follow actually the Markovnikov's addition, right? And so you can have your H and water as your agent. That is the hydration process, which means you have your acid catalyzed hydration process, or you can follow the oxymercuration demercuration process. So if you want to follow the Markovnikov's rule, you can use this. But if you have the anti-Markovnikov addition, meaning this one is the carbon which contains a higher number of hydrogen. No, you have your duha hydrogen. This one is isa lang hydrogen. And you look at here, supposedly in the Markovnikov, this is where the hydrogen should be added like this. So you have your CH3, and this is where the OH. But if you get like this one, a primary alcohol, it follows the anti-Markovnikov addition. Okay, so you get a 1-degree alcohol instead of a 2-degree alcohol. So for this kind of product, then you would opt for the second, or for the other reagent, which is the hydroboration oxidation reaction. So you have your BH THF and H2O2. You always have to know that H2O2, the hydrogen peroxide, is always an oxidizing agent. Okay, so this one follows the anti-Markovnikov rigid selectivity. Okay, so before I proceed, can you ask someone, Donna, if we have our reactant 1, 2, 3, 4. So this is butene 1, 2, 3, 3, 3 dimethylbutene. And if you want to prepare 1, 2, 3, 4, what is the name of this? 1, 2, 3, 4. What is the name of this alcohol? 1, 2, 3, 4. So you end with, it's the name of this, Donna. Donna? Wala si Donna natulog. Ronel? What is the name of this? Ronel. Natulog si Ronel. So let's call another.
Kuan ma'am tuda.
What's the name of this?
Kuan ma'am for pentanol.
What? Pentanol? You have 1, 2, 3, 4. 1, 2, 3, 4. The longest continuous
Kuan ma'am butane.
the longest continuous carbon chain containing your OH. Now you have this one. So you expect this to be 1, 2, 3, 4. So but, you end with all. So how do you name? Your parent chain would be, your parent chain would be, your parent chain would be Ansa Ronald? Akin sa to Ronald di ay. Ansa to Ronald?
Parent chain of butane.
The parent chain is butanol, right? 1 butanol, 1, 2, 3, 4. And this one, how do you include it? Include this one in your name. So you have your 1 butanol and
3
your
dimethyl, ma'am.
3
dimethyl.
3 kay duha man. So 3 kaduha na to i-mention. 3 di kay duha man.
3
methyl tapos 1
butanol, ma'am. 1 butanol.
1 butanol. Okay, so is it a 1 degree, 2 degree, or a 3 degree alcohol?
1 degree.
1 degree?
Yes, ma'am.
Okay, it's a 1 degree alcohol. Now, if this will be our product, start coming from the starting material, then I would like to ask Donna, what is our reagent that is used to prepare this one? What do you think? Does this one follows the Markovnikov addition or not? So that will be one question. Once you have your HOH added to your alkene, does this one follows the Markovnikov addition? Yes or no? Donna, does this first product follows the Markovnikov addition? Yes or no? Donna? Wala, natulog si Donna. Ronald. Natulog po si Ronald. Okay, so I'm gonna call.
Yes, ma'am.
So my question, Ronald, is on the starting material to this first product. Do you think that this pathway or this kind of reaction follows the Markovnikov rigid selectivity? Yes or no? Ronald? Unsa man? Ang tubag, yes or no, Ronald? Nadunggan ba ko? Are you with me? Anyone?
Yes, ma'am.
Okay, so nakita to ninyo kung akong question kanina. Asa day ang uban? Okay, so for question number 1, ay reaction number 1, akong question, Ronald. Kani nga product atong giingon ni Ronel nga 3,3-dimethyl 1-butanol. Having this product, kani, does this pathway or does this reaction follow the Markovnikov's rule? Yes or no? The answer, Ronald, is yes or no, Ronald? Tamaglangan. Ronald? Naminaw
Yes,
si
ma'am.
Ronald.
Walang signal, ma'am.
Okay, si Shaira na itong pangtanan na. Di mo makita ang slides. Ikaw na lang answer sa sunod question, Ronald. The next question is, what would be the koan? So, Shaira, I just want to know if it's yes or no. Does the first reaction follow the Markovnikov's rule? Yes or no?
No, ma'am.
No? So, if no, it follows the anti-Markovnikov's rule, then I would like to ask Ronald, unsa kaha ang posibleng nga reagent, Ronald, for us to obtain this product coming from this reactant? Balik ta. You can, anyone? You have only 3 options, no? You can use the acid catalyzed hydration of alkenes. You can use the oxymercuration, demercuration, or you can use the hydroboration oxidation process. So, akong question now is, unsa man ang reagent na pwede na ito magamit? So, since you are soon to be chemist, no? I would expect, or it is expected, that you would know the kind of reagents that would be useful or that would be used to obtain a desired product. So anyone, what can you suggest as your reagent to be used if we produce this? Ano ni mo? Ay, mauni siya kung ako rin na siya. So, ang reagent, gani ang magamit? Anyone? Wala? Chapter 8 raman taon ni ay. Tulora. So, first, the mercury, the hydration reaction. H plus means acid. Of course, once you have your acid, like H2SO4, no? That is a strong acid in water. It completely dissociates in water to form your H3O plus or H plus. More na siya. The H plus is always hydrated with water, so it always becomes H3O plus. Second reaction is the oxymercuration, demercuration, and the third reaction will be the hydroboration oxidation process. So for the first one, you can have your for this one, your agent will be ansaman. Since ingon si Shaira, this is the anti-Markovnikov. Okay, if you look at in here, this one is the anti-Markovnikov. So what is your agent? What would be your agent? Shaira. Shaira, your internet connection is unstable.
B8 kanang BH3 THF. Ma'am?
Okay, so you will have your BH3, THF, and the second step will always be the oxidation process. If you remember in your chapter 8, no, BH3 can always also produce your alkanes. The alkanes from there. And the second one, what is the name for the second one? Kamo na lang duha. So of course, Ronel, are you here?
Yes, ma'am.
For the second reaction, does this follow the Markovnikov or the anti-Markovnikov rule for the second synthesis?
Markovnikov.
You have the Markovnikov's rule. It follows the Markovnikov's rule. So what are your possible reagents?
Yes, ma'am.
What is a possible reagent that you'll use to prepare this product? This is 1, 2, 3, 4. So this is the name of this. This is 2-butanol. You have again your 3,3. So you have your 3,3 dimethyl 2-butanol here. So what will be your reagent?
Itong kuan, ma'am, mercury.
So ano sa mercury? Ano sa mercury to? Daghay mercury, no? So you always have to remember what state of mercury. So you can use the common one is the mercury acetate, OAC 2. Okay, in the presence of water and THF. And the second one is the reduction, which is sodium borohydride in the presence of hydroxide. So at this point, since we'll be using this three kind of reactions, and this is addition reaction, no? I'd like you to review again on chapter 8 so that dili mo mawala when you want to prepare your desired alcohol. Okay, so if you want to prepare it, would it be a 1 degree, a 2 degree, or a 3 degree alcohol? So question, Ronel, is this a 2 degree or a 3 degree alcohol?
2 degree, ma'am.
The 2 degree
2
alcohol.
degree.
Okay, then the next one will be once we were able to prepare, preparation of this alcohol would often lead to the synthesis of another kind of product. So for now, again, so for the second reaction, there is two kinds of reaction that you can use. The second, you have your 2-butanol, you have 3,3-dimethyl 2-butanol. You can use the acid catalyzed hydration, or you can use the oxymercuration, demercuration. Katayong giingon, HG acetate in the presence of THF and water, and then you have the demercuration will use the sodium borohydride. Okay, so I don't want to dwell on this because we have already talked on the mechanism of this in chapter 8. So if you want to review again, you go back to the video, to the discussion. And at this point, we'll focus on the reactions of alcohols. So once you have prepared your alcohol, for instance, from another starting material, and you have your alcohols, the alcohols will then be used to, again, another starting material to prepare another compounds, And in such a way, alcohols will then react in a different, there will be a different kind of reactions that alcohol would undergo. Okay, so the reactions of alcohols have mainly to do with the following. The oxygen atom of the OH is nucleophilic and nucleobasic. I think we have already know this from the very beginning. Oxygen once you always have your OH, no, or oxygen atom, you always know that there are electron pairs, unshared electrons on oxygen. Dili lang mapakita whenever we show in our slides, no? Kapoy kayo may show sa unshared electrons, but know that there will always be unshared and unpaired electrons on oxygen atom, along with the other heteroatoms like your nitrogen, oxygen, your halogens. Okay. And the hydrogen atom of the OH is weakly acidic. What do you mean by weakly acidic? It can, okay, between oxygen and hydrogen, oxygen would bear the partial negative charge, being an electronegative atom. So we put a partial negative charge on oxygen, and hydrogen will bear a partial positive charge. So between the bond between oxygen and hydrogen, the electron density will be more directed to oxygen, or the dipole between oxygen and hydrogen will be directed to oxygen, being an electronegative atom. So you expect your oxygen to be partially negative and your hydrogen to be partially positive. So in this way, being partially positive hydrogen here can also be acidic. So your OH can be acidic. The hydrogen in your OH is weakly acidic. And the second one, third one, the OH group can be converted to a living group so as to allow substitution or eliminations. We have learned in, I think in chapter 3, no, when we were talking about the nucleophilic substitution, the OH can also be converted into different functional groups. Now, it would depend kung unsa po ang atong reactant. And the OH can be converted as a living group. And I think we have already discussed it in the previous chapter. And the only way for the OH to be a good living group, we have discussed that in the introduction of this Chem 121. In order for the OH to be a good living group, it has first to be converted or protonated, no, to become a good living group. Okay, so this is an example of an alcohol. This is 1, 2, 3. So this is 2-methyl 2-propanol. Okay,